We are now recording. Let me think if there probably a few things have changed since we last spoke, because I'm still learning the ins and outs of all this stuff. A little bit of history here. When we started, I thought I would do everything on announcements because that's how we used to do it on the old blackboard. So I started doing that, and then I found that little tab that was up there at the top that was messages. I said, oh, and when I used it, it looked just like it did, or pretty much like it did with the announcements, but it had a few more features. I thought, oh, this is just a shortcut for the announcements, and it's easier to get to the features. So I started doing everything on the messaging. And also I was getting messages from students there, so I started doing that. Then I found out that some students, because I had started on announcements, weren't checking messages, okay, and therefore missing some stuff. So I decided, well, I'll start doing both, announcements and messaging. Especially after yesterday when I found that one student, he said, I can't get the message that you sent. I said, well, look for that little envelope. He said, there isn't a little envelope. I said, he kept talking about his mobile device. I said, well, what mobile device are you using? So he held it up, and it was a pad. It happened to be an iPad. And he held it up to me, and sure enough, the gray box at the top of the screen, or near the top, that had the envelope in it and all the other little icons, had no icons at all. And I couldn't tell him what to do with that. So I advised him to go see some of the people who knew more about things like that than I did. But I said I'll start doing everything on announcements. So last night I started doing only on announcements. But then I found out you can't attach an email to or you can't attach anything to an announcement. So then I was stuck again. So now I'm going back. All things that are purely announcements are going out only through announcements because that's all some people can get. And things that I have to send an attachment, like a test or something like that, I'm going to have to do that through the messages. So if I said one thing yesterday or earlier in the week or last week, it probably has changed because I'm still finding out limitations of this Blackboard Ultra. So anyway, that's how we're going to go from here. Any questions about anything? I know Dawson's heard it a couple of times. Josh, you know that summer courses are going on to be only virtual classes like this one. We're not going to be back on campus again in the summer. There will be some online courses, but those are very few, the ones we normally would be offering. But all the rest of them will be virtual classes, just like this, virtual classrooms. We meet at a certain time, students, instructors together, go over things, work things out on the board like we've been doing. Any questions about any of that? Okay. All right. In addition to classes being virtual, all of the functions of the college are trying to become. They will be, and there are still some of them getting there. For instance, if you want to get in touch with the business office, there's now an email address for that, just business office, written as one word, no spaces, no anything's in there, business office at lawsonstate.edu. The records office, records at lawsonstate.edu. I imagine financial aid has one like that. Sometime earlier, probably a week ago or so, the dean sent out a whole list of phone numbers and emails for various offices. Check that. That's under messages, I believe. Okay? I don't believe I sent that as an announcement. Okay? So check your message box for that. Also, the library sent a link. Check that. You can get to the library, any services there. And they're going overboard trying to get everything to be virtual. The business office address wasn't on there, so I gave you that one. But just about everything. Oh, advising is going to be virtual, completely virtual. What you do, you go to the new advising center, you click on it, you sign up for an appointment. You may not get your old advisor anymore, okay? But there will be someone there. I think the hours are 8 in the morning until 7 in the evening. There's going to be someone available for advising someone Monday through Friday. Okay, Friday at 7, I don't know how much business they're going to have, but since nobody can go anywhere anyway, why not be there? Okay, so everything. Now, I think this means you probably are going to, if you're used to your advisor putting in your schedule for you, I think you're probably going to have to do that yourself, because I don't know if we can be on Zoom and working the faculty suite or the student suite at the same time. Maybe we can. I don't know. I haven't done it. I haven't tried. But really the advising is mostly for advising, figuring out what you want to do. You might have to put in your own schedule. So any questions on any of that also? College is trying to do everything it can to be as much like we're on campus as possible. We just can't be on campus in groups yet. And this is becoming, well, actually the cases in Alabama are increasing like crazy. That's mostly because we just started testing. So I think my wife said this morning we have over 1,000 cases in Alabama right now. Just 2 or 3 weeks ago we thought we had 0, and they were saying you can't go to out of state. Faculty couldn't go out of state because you could bring it back. I thought to myself, it's here, you just haven't measured it yet. And sure enough, that's the case. And the deaths are beginning to pile up too. Alabama actually has done better on the death thing than most other states have. I think there's been a big pocket down around Auburn. Seems like there's been several deaths down in that area, but I don't know if UAB has had more than just a couple. I don't think they're in double digits yet. Nationwide, though, we've had the most deaths, I think, recently than we have. So no matter what you're hearing, things are not looking good on the national scale. So there's no going back this summer. I'm beginning to worry about the fall, but we'll worry about that later. Okay. Any questions on anything then, including linear algebra? That's what we're here for. All right. We're in Chapter 3, Determinants, in Section 3.3, which is Properties of Determinants. And we've been talking about the last theorem we covered was the determinant of an inverse matrix, and that turned up to be a really handy little thing. The determinant of an inverse matrix is the inverse, in other words, the reciprocal of the determinant of the original matrix. Pretty handy. So example 4, that's where we're starting on page 129, near the top of the page. Find the determinant of A inverse. Let me get my pen set up. Okay. For this matrix, here is A, is this matrix here, 1, 0, 3, 0, -1, 2, 2, 1, 0. Blast off. Okay, my pen is very, very, very slow. Okay, but it wound up writing. Okay, I think I wrote it right. That first 0 up there is pretty ugly, but understand that is a 0. Okay, I didn't make it much better. So it says find the determinant of the inverse of that matrix. My question to you, how would you proceed?
On the inverse.
Say again?
On the inverse.
Okay, finding the inverse. I can tell a hardworking student when I hear one. You certainly could do that, and in fact, I contend this looking familiar enough. I was almost about to guess. I think we have found the inverse of it. Oh, maybe we haven't. Okay. That is one way to go, but how do you go about finding the inverse?
It was underneath matrix.
Okay, exactly. So what we would have to do is do that and then start our row reduction. Now, I've got another question for you. What do you find easier to do? Finding an inverse or taking a determinant?
Taking a determinant.
You find that easier? Well, then my contention is, why don't we just take the determinant of A, and then we can just find its reciprocal, and you found the determinant of its inverse, right? But you're a hard-working guy, and I don't want to discourage you from that, but I'm a lazy guy, okay? So to me, that sounds like a better choice. So rather than writing this down, what I'm going to do is erasing this and that, and probably this. I'll come back to that in a minute. In fact, I'll write it down below probably. And now let's do a determinant of this. Now, I think we've done this one before. There's a couple ways to do it. We could expand it, and that would be pretty easy to do. Or we could do a row reduction on it first. Which would you rather do, expand or row reduce?
Expand.
Expand? Okay, let's go on and expand it. So tell me what to write.
Add a 1, 0.
1, 0 on the top row.
0, -1.
0, -1.
2, 1.
2, 1. Okay, now I'm going to put the determinant bars on. I know that's not a square matrix. You can't really do a determinant, but you know what I'm talking about. This will be what?
0.
0. This will be
0.
0. This will be
0.
0. Let me erase those. That was pretty easy. So I think you made a good choice of doing expanding. Okay. This one will be
6.
6. This one will be
-2.
-2. And this one will be, oh, think hard on that one. 0. So this will be 4. You're right, that wasn't too hard. So what is the determinant of its inverse?
1/4.
1/4. That was pretty easy, wouldn't you say? And that's exactly what they got. Okay. Now, do you want to try it the other way and just to check it? Yay or nay?
I feel confident.
What's that?
I feel confident in the answer.
Yeah.
But we didn't try the other way. So. I need to see how you do the. I'm still kind of confused on how you do the. Like another row reduction, but how you find the 2 by 2 to do the differential.
Okay. Oh, okay. Oh, you're talking about the other way of doing the determinant. Is that what you mean?
Yeah, like how you, when you find like the 2 by 2 inside of the 3 by 3 or whatever.
Okay. Now is this Dawson or Josh?
Dawson.
Oh, Dawson. Okay. Do you want, is what I'm asking, is what you're asking, you would like to see this done the other way?
Yeah.
Okay. Without row reduction. Is that right?
Yes.
Okay. That's a very legitimate thing. Let's do, and you want matrix A, you don't want to do the inverse first.
No.
Okay. Right. Okay. If you were going to tackle this by what they call the cofactors and the minors and all that kind of stuff, okay, without doing the expansion, okay, what you do is pick a row or a column, okay, and typically what I do is the one with the most zeros in it. But this one just happens to have 1 0 in every row and 1 0 in every column. So it really doesn't matter which one you choose. You pick either a row or a column. They all have 1 0 in it, so pick one.
Column 1.
Column 1, that's what we're going to be using, okay? So we start at the top with this 1 here and do its minor, you must say. But first I'll say, what is the sign of that position?
Positive.
Positive. So that's just going to be 1 times this, the determinant here. So let's just do that determinant. What's that determinant?
-3.
Not -3. You're multiplying. That's 0 minus 2. So that's going to be a -2, right? Do you agree? Okay. All right. So let's get all those construction lines out of the way. Okay. Okay. Now we're going down the first column. That's what you said. We would next go to the 0 here. Okay. And if that were anything other than a 0, this would be in a negative position. So you would put negative whatever number that was. If that was a 7, you would put a -7. If it was a -3, you would put a +3. Okay. And then you would do the determinant, wipe out this row and column, and do the determinant of the square matrix that's left, the 2 by 2 that's left. But that's not the case here. That's a 0, and because it's 0 times anything, that's why we chose the row or column with zeros in it. In this case, it didn't matter because all of them had them. That's why we chose it, because it makes it easier. So we'll go on to the third one. What is the sign of that position?
Positive.
Positive. So we're going to do a +2, that number to there, times the determinant up here. And what's that determinant?
3.
+3. 2 times a +3. So this is -2 + 6 equal 4. Same thing we got before. Does that answer your question?
Yeah.
Good. Okay. Any others? All right. That was example 4, done a couple of ways. So let's move now to, all right to erase? Okay. The equivalent conditions for a non-singular matrix. Okay? Now what's another word for non-singular? Most of the time we use that other word and we don't use non-singular. We put non-singular in parentheses. What's the other name for a non-singular matrix?
Square matrix.
It was sort of in example 4, the 1, 2, 3, 4, fifth word in there. If you got your book in front of you. The fifth word in the title of that was inverse. The other name for non-singular is invertible. Equivalent conditions for an invertible matrix or a non-singular matrix. Okay? Here's what the requirements are. First, okay, to be invertible, the matrix has to be square. Okay, so A has to be an n by n matrix. Okay, a square matrix. Okay, now, that's where you start. Now, the first one is exactly the thing. Equivalent conditions for a non-singular matrix, that means A is invertible. That's what non-singular means. A is invertible. Okay. Or non-singular. You could have said non-singular as well. Now, that means exactly the same thing. This is exactly the same statement. It's just phrased differently and longer. Okay. If you have A times vector X equal vector B, that matrix equation has a unique. If A is an invertible matrix, a non-singular matrix, then A has a unique solution for every n by 1 column matrix B. That B right there. Whatever, if A is an invertible matrix, and X is, of course, your variable matrix, that would be X of 1, X of 2, X of 3, up to X of n, then whatever B you put there, there will be one and only one solution for that equation. Put a different B, of course, it's a different solution. But every B, whatever B you put there, will have a unique solution. So that's another way of saying that A is a non-singular matrix. Or if A is a non-singular matrix, that statement's true. Now, this follows directly from there. AX, if AX happens to equal, and this, they keep missing this, that is a zero vector, okay? Not the number 0. It doesn't look bold at all to me, okay? But this has only the trivial solution. Now that follows exactly from the one right above it, because the one above it says it has only one solution, okay, a unique solution. And if that B is all zeros, then I guarantee you that X equal all 0 will solve it, but because it has to be a unique solution, that means that's the only solution it'll have, the trivial solution. All the X's have to be 0. Okay, so that's an equivalent expression for saying A is invertible or non-singular. The fourth one. A is row equivalent to the identity matrix. The I sub n, same size. Okay? Now, remember what that was, that there's every non-singular, well, I'm going to get into the next one. It is row equivalent to the identity matrix. How we found our inverse? We reduced this down to the identity matrix, right? That's how you did it. If you'd have done it Dawson's way, we would have then augmented the matrix that we had, A, with the identity matrix of the same size, then done row reduction. A would have become an identity matrix itself. The old identity matrix happens to become the inverse of that matrix, so that means it's row equivalent with the identity matrix. And that's how we found our inverse, okay? If it's invertible, it's got to have that, okay? Number 5. And this is the one we did in, was it the first of this chapter or the end of the last chapter? In the last chapter, I think. The A can be written as the product, and I don't know why it writes some words and doesn't write other words, okay, as the product of elementary matrices. Now, that was what we did, like I said, I think it was the end of the last chapter, because every step you did to row reduce it to the identity matrix, that step can be expressed as a elementary matrix itself, an action on an elementary matrix, and the product of those then gets you back to A, or of their inverses or something like that, okay? It can be done. And 6, can't get the, okay? Here is this one, the most recent. The determinant of A is not 0. Well, that's almost the simplest one. But sometimes If it's a huge matrix and very big or strange or fractional or other thing numbers, that might not be an easy thing to do either. But then probably none of these other things are going to be easy either. But those 6 statements are all interchangeable. They all mean the matrix A is non-singular or invertible. Okay, so let's go to example 5. Any questions on that before we leave it? All right, going to example 5. Which of these systems has a unique solution? So here's the A. 2x2 minus x3 equal -1. 3x1 minus 2x2 plus x3 is equal to 4. And 3x1 plus 2x2 minus x3 is equal to -4. Or the B one looks exactly the same. 2x of 2 minus x of 3 is equal to -1. 3x of 1 minus 2x of 2 plus x of 3 equal 4. And 3x of 1 plus 2x of 2 plus x of 3 is equal to -4. The question is, which of those systems, if either of those systems, has a unique solution? Now, this is a system of equations. It's not as simple as any of the things that we were just writing down, but which of those criteria before? If this has a unique solution, that means its coefficient matrix is invertible, okay? That is the bottom line here. So basically, that's the easiest thing to do, is look at the coefficient matrix and see if we can determine if it's invertible or not. So these two matrices are awfully close to each other. I'm going to call this one the A matrix, because that was little a here. And this will be, you tell me. Earth to class, come in please. 0. 0. 2. -1. Okay, let's just stick with the coefficient matrix for now. We could do the other way, and that's a perfectly legitimate way to do, but this is actually, I think you'll find, a little easier. Let's just look at the matrix, the coefficient matrix. What's the next entry?
3.
I got the 3. -2. 1. 3. I can't get it the right way. 2. -1. Okay. Now put that as a matrix, and that's fine. But really, in this case, the easiest thing to do would be to do its determinant. But before I would do its determinant, I would note that you can do a fairly simple row reduction or column reduction. You see, if you were doing, like you were suggesting, augmenting this with the constants at the end, you can only do row reductions on those. But in doing determinants, you can either do column or row reductions. And this will actually work best if you do one simple column reduction. What would that be?
2 column 3 plus column 2.
Okay, it's the new column 2. And what would that give you in column 2?
Give you all zeros.
All zeros. And then could you tell me what the determinant of that matrix would be? Well, the determinant of A would be 0. And what can you conclude by that?
There's no inverse.
Not invertible. So therefore, this will not be a unique solution for that set of equations. Number one, it may have no solutions, or if it has a solution, it would not be unique. Okay? Now, you will have dependency there. Let's do the same thing with this one. And that starts off the same, 0, 2, minus 1. 3 minus 2, 1. Come back. Okay. 3, 2, 1. Now, looking at that, I'm going to call this one B. You can call it anything you want to. I just chose to call it B. Again, I would start doing the same thing we just did because it was so easy. Do that same, because I'm going to look at determinants now, because all we're interested in is, does it have a unique solution? And if it has a unique solution, that means this has to be an invertible matrix. So that's all we're looking for. Is that an invertible matrix? And the easiest thing to determine in this case is its determinant. And let's do the same row reduction you did before. 2 times column 3 plus column 2. Okay? And this is no longer going to be the matrix, but the determinant of the matrix. That's going to be, and this should be a determinant too, and this should be a determinant here. Okay. 0, 0, negative 1, 3, 0, 1, that's a 0 there, and 3, okay, yeah, 4, 1, right? Now, you have a choice here. Always have a choice. Sometimes they're all bad. Okay, but this one's a pretty good choice. What would you choose?
Find the determinant.
Yeah, to find the determinant, that's what we're doing. That's why I put the straight bars there. You can't do column reduction if you're not doing a determinant. Nothing else allows that. Determinants do allow it, okay? So to get the determinant here, what would you do?
I'd put the line through column 2.
Say that one more time.
Put the line through column 2.
Oh, through column 2. That's perfectly fine. Okay, you're going to use column 2 to do your reduction. The only non-zero entry there is that 4. What is the sign of that position for 4?
Negative.
Negative. So its determinant would be a negative 4. And I think I'll write it down here just because it is. Since I'm using that one, what's left is a 0, negative 1, 3, 1. Okay? That's a pretty easy determinant to do. What does that give you? That's a pretty ugly negative 1. It's what?
Positive 3.
Okay. So you have negative 4 times positive 3, and that gives you negative 12. Perfect. I don't care what it is, as long I really am more interested in what it's not. What's all we're interested in?
If it's
That's
zero.
not 0. Negative 12 is definitely not 0. So we do know they didn't ask us what the solution was. They just said which one has a unique solution. B does. Okay? Now, if you want to be real picky about it, if you just look across at page 128, the top of that, actually, example 3. Example 3 was exactly this problem. Okay? Those were the two matrices they had, and we determined the first one had a determinant of 0, the next one negative 12. What we hadn't done is extend that to mean that a system of equations with that set of coefficients then would be non-unique for the first, may not even exist for the first, but it would be a unique solution for the second. No matter what the constant column would be. No matter what the constant column would be. And that's basically what number 2 says. AX equal B is a unique solution for every n by 1 column B. So you sure? Negative 1 for negative 4, that will have a unique solution for B, would not for A. Okay? Whatever you put in there for the column matrix of B would have a unique solution. All right. Now, a few more, and again, the title of this section are Properties of Determinants. Let's go around to determinants and the transpose of a matrix. Okay? Do you remember what a transpose was?
Whenever you just make it's like you make the rows the columns.
And the columns rows, exactly. Only do it to square matrices for what we're doing here, taking a determinant. You can transpose any size matrix, but what we're talking about here is the determinant of a transpose. That has to be a square matrix. So that's where we start. A is a square matrix. Okay? If that's the case, then, and it doesn't say it has to have a determinant either, the determinant of A is equal to the determinant of its transpose. Okay, I started to write the wrong thing. If you exchange the rows and columns of any square matrix, whatever the determinant of the first one was, when you exchange the rows and columns, that'll be the same as the determinant of the second one. Okay? That's not a row reduction situation. You know, remember, those were not the same. They're similar. I mean, they're related, but not equal. For a transpose, that's equal. So let's do example 6, which you can also find at larsonlinearalgebra.com, interactive version for this type of an example. Okay, and they want us to show this. So I'm going to erase this so we'll have more room to write. Here is A. Three, 1, negative 2, 2, 0, 0. Thank you so much. Minus 4, minus 1, 5. What is the determinant of A? How would you do it?
Put the line through row 2.
Through row 2, is that what you said? I agree completely. And what would be its determinant then?
Would be 2 times.
Okay, I can't hear well.
2 times.
Okay, wait. You first ask yourself what's the...
So the positive position.
Is that a positive position? Plus, minus. Plus, minus, plus, minus. Plus, minus, plus, minus, plus, minus, plus, minus. Plus, minus, plus, minus, plus, minus. Any way you do it, that comes out minus. That's going to be a minus 2 times the determinant of what's left over. And what is left over? 1, negative 2, negative 1, 5. Okay, so this will be negative 2 times, I'll put that as just a times,
5 minus 2 is going to be
5 minus 2 is 3, right?
so negative 6.
Negative 6. Okay, I'll buy that. Didn't cost too much. So let's now do a transpose. What would that be? Wait. 1, 0, negative 1, right? Second row, second column becomes the second row, right?
Yeah.
Okay.
Negative 2, 0, 5.
Okay. So what would be the determinant of A transpose? How would you do that?
Line through column 2.
Yes, use column 2. And then what would you do? Negative 2, perfect. Times what matrix is left?
1, negative 1, negative 2, 5.
Okay. And what's that?
That is 5 minus 2, so that's negative 6.
Negative 6. Perfect. You got it. So at least for this matrix, it's equal to, the determinants are equal. Okay? And I think you'll see that's always the case, because all you've done to change, you get to choose whether you row reduce or column reduce, and whichever one you did before, you just do the other, and the numbers are exactly in the same order. Okay? So they've got to be the same. I was sort of surprised they didn't do a little proof for you there, but they didn't. So anyway, that's done. Now, here's another linear algebra applied. They talk here about systems of linear differential equations often arise in engineering and control theory. I'm not exactly sure what they mean by control theory. There are things called controllers that they use electrically or electronically, and that sure sort of looks like what this picture is talking about, but I can't tell for sure. For a function f of t that is defined for all positive values for t, you can use the Laplace transform, which then changes to another variable s, and that's the integral from 0 to infinity of e to the minus st times f of t, then dt, provided that the improper integral does exist. Laplace transform and Cramer's rule, which uses determinants to involve system equations, can sometimes be used to solve system of differential equations, and Cramer's rule is coming up, I think, in the next section or the one after that. Okay? So, in fact, in this course, they're going to have, in fact, if you look at the back of the book, I think it was in the back of the book, maybe it's not anymore. Right before the answers, maybe I'm wrong. Thought there was an appendix. Maybe it's in the front of the book. No, maybe I'm wrong there too. Nope, sorry. I'm thinking another course. Okay. Sorry. Okay. I guess it was the differential equation course. Gets into Laplace transform, because that's what you do in solving differential equations. So anyway, forget that. Homework exercises here include in section 3.3 Any of the odds 1 through 5, all those should be at calcchat.com and in the back of the book as well. Any of the odds 7 through 13, they should be at calcchat. The difference, the back of the book just gives the answer. The calcchat gives you worked out solutions to the odd number exercises. Not just the answer, but how the steps you take to get to the answer. 15 or 17 should be at calcchat. Any of the odds 19 to 23 should be at calcchat. Any of the odds 25 to 29 should be at calcchat. 31 to 35 should be at calcchat. 37 to 41 should be at calcchat. 43 through 49 should be at calcchat. 51 to 55 should be at calcchat. 57 should be at calcchat. You have a proof, 59 should be at calcchat. And I'd say any of the odds 61 through, and there's quite a few of these, 69 should be at calcchat. Now there are a couple of those are proofs also. There's a true false, 77 should be at calcchat. Orthogonal matrix. Now this is one thing that kind of bugs me about this book. An important topic, or at least in my mind it's an important topic, is not mentioned in the text, but brought up in the exercises. And that just seems like a weird place to do it. But now they introduce what is an orthogonal matrix in the exercises and has you do exercises with that. And here's the definition of an orthogonal matrix. If you have an invertible matrix, okay, A, of course that means it has to be square, but it also has to be invertible. That square invertible matrix is orthogonal also if its inverse is equal to its transpose. Weird set of circumstances, but that's true. So exercises 73 to 77 depend on that. 79 also follows that definition. All those should be at calcchat. And 81 uses that. 83. Oh, here we have something else. And I think we hit this earlier. I just don't remember where it is. And idempotent. I don't know if that's pronounced idempotent, idempotent. I don't know how you pronounce that. But here they give the definition of it in this one little phrase here. If a squared is equal to a, it's idempotent, or whatever that is. Okay? So 83 is a proof that deals with that. So now we move to 3.4, applications of determinants. I think this is the last section in the chapter. Let me just check on that. Yeah, it is the last section. Applications of determinants. Okay, we're going to start with something, at least in my mind, it starts off being fairly complicated. Okay? It's the definition, it's talking about the adjoint of a matrix. Okay? Now, just as a reminder, we've talked about the inverse of a matrix, the transpose of a matrix, the one thing or another, all the different things you can do to a matrix. Here's another one, the adjoint of a matrix. Okay? And it's using determinants, so we're going to get there. Okay? They have a few words at first. So far in this chapter, you have studied procedures for evaluating and properties of determinants. In this section, you'll study an explicit formula for the inverse of a non-singular matrix and use that formula to prove a theorem known as Cramer's rule. Okay, that's coming up, not yet. You'll also use Cramer's rule to solve systems of linear equations and study several other applications of determinants. Now, leading up to that, it says, recall from section 3.1, at the very beginning of this chapter, we talked about what the cofactor was. Okay? The cofactor, Cij of a square matrix, A, would be the sign of the position, that's part of it, times the determinant of the matrix obtained by deleting the ith row and the jth column of A. And the matrix of cofactors then has this form. Now, cofactor was not a simple thing to do. I mean, it's not all that complicated, but you start with that sign, plus or minus, and then you, with that sign, you calculate the determinant of everything other than the row and column that cofactor that you're doing for the cofactor, and that is then the cofactor of that matrix. So with each of those, now that's a terrible description, but for each cofactor that we got that way, then you put the cofactor 1, 1, cofactor 2, 1, okay? No, I'm sorry, 1, 2, I was looking down, I was going to say that's not right. I was looking at the wrong line in the book. Okay, cofactor 1, 2, cofactor 1, 3, dot, 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 up to cofactor 1, n. I think it's an n, yeah. They sometimes change. Cofactor 2, 1, cofactor 2, 2, cofactor 2, 3, dot, 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 to cofactor 2n, cofactor of 3, 1, cofactor of 3, 2, cofactor of 3, 3, dot, 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 to cofactor 3n. We'll dot, dot, dot this down to get cofactor of n1, dot, 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 down to cofactor of n2, dot, 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 down to cofactor of n3, and dot, 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 and dot, 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 and everywhere dot, dot, you get cofactor of n. So there's the matrix of the cofactors. And each one of those you have to calculate from the matrix A. Okay? Not a trivial thing, because every one of those requires a whole calculation. Every element in there requires a calculation. Once you get that, then the adjoint, and there's no abbreviation for that, like the inverse function is to the minus 1. The transpose is to a t. Multiple is you just do the power that you're doing it to. Determinant, you put the parallel bars, vertical bars around it, okay? The adjoint doesn't have a special symbol. You have to write ADJ of that original matrix A that you got those cofactors from. This is adjoints of matrix A. You start with that, and then the adjoint would be the transpose of that cofactor matrix. So that would be C11, C21, C31, C dot 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 to CN1, C12, C, ooh, that's ugly. 22, C32, dot 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 to CN2, C13, C23, C33, dot 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 to CN3, dot 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 down to C1n, dot 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 down to C2n, dot 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 down to C3n, and then a dot 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 everywhere dot dot to CN. That's a cable news network. Never mind. Okay. That's how we define the adjoint of a matrix. And you would think, what in the world would be worthwhile to go through all that to find such a thing as this? Okay? And I'm not sure I'm ever going to answer that question sufficiently, but let's go on and calculate one. Okay? Big a pain as it is, let's do it. Okay? That will probably eat up almost all the time we have left. So we want to find the adjoint of A, and here is A. Thank goodness it's only a 3 by 3, but that's going to be bad enough. -1, 3, 2, 0, -2, 1, and 1, 0, -1. No, -2. Okay. Dumb things like this can really throw a problem into a tizzy here. All right. Now, first we've got to calculate the cofactor matrix, the matrix of cofactors for that matrix. So, do they give this a symbol? They really don't. I'm going to call it C, just for lack of anything else to call it. Okay. Now, it's going to be a 3 by 3, but every element in here has to be calculated from this. So, that first element there is a positive position, so we use a -1 times the determinant of this thing down here. And that would be 4. That would just be 4, so that would be a -4. So that's going to be a -4 here. Okay. Now, would you forgive me if we just go straight to doing the adjoint? Or would you rather have the cofactor matrix first? You answer me that.
Just go straight to the edge.
Say straight to the adjoint?
Yeah.
Is that what you said? Okay. Because all you have to do is do the transpose of what we were going to do. The -4 is right no matter which way you do. A1 or C11 is going to be right there. Okay? So, what I'm going to do next, or I'll let you decide. Okay? Okay? Do you want to do, and this is going to be, let me go on and change this. This is what you've chosen to do now. The adjoint of A is going to be the transpose of the cofactor matrix, or the matrix of cofactors. It's not the cofactor matrix. So we're going straight to this. So you tell me, do you want to start going rows or column? I don't care, but you pick what you want to go to next. You want to go position 1, 2 next, or the position 2, 1 next? I really don't care. Here in matrix A, you want to go to the 3 next, or you want to go to the 0 next?
1, 2.
Which one? The 3? Is that what you said? Okay. Let's go to the 3 now. Now, understand, we're going to be writing the answer in the other position, okay? Because we're going to do the transpose. So let's take the 3. What is the sign of that position?
Negative.
-3 then. And we'll wipe out this row and this column, okay? And then the determinant of what's left is a -1. So that's going to be a 3. So that's what we're going to put there because we're at the same time doing the transpose. Okay? Am I okay doing it this way? Because I'm being really, really lazy. Okay. Okay. I could leave them all here because they're not taking that much room to write. Okay. Oh, I meant to do that one too. So I assume we're going on across. Going on across. This is aggravating me like crazy. I go and get the eraser, and it comes back the pointer. Okay. All right. So since we're going this way, we're now going to do the 2 up here. What is the sign of that position?
Positive.
Positive. So that's going to be a +2. And when you do the matrix down here, what do you get? 2. So this is going to be a 4 down here. Agreed? Okay. All right. This is a lot of erasing, but if I don't, it... Yuck. Pick on the eraser, and it does nothing. Okay. Except make a mess. Okay, we got the first row done. I'll go and erase that. Okay. Now let's go down to the second row. So we'll do this. And what's that going to be, by the way? 0. So we will put that one just in as a 0. All right, that was so easy. Let's now erase that one and write in this one. What's the sign of that -2? The sign of the position of -2.
Negative.
Now the position is positive, plus, minus, plus. Remember your diagonals always, main diagonal is always plus. Okay? So plus, minus, plus, or plus, minus, plus, or plus, minus, plus, minus, plus. Plus, minus, plus, minus, plus, minus, plus. It always comes out plus. Okay? So that's going to be a -2 times, that one would be a 2 0. So this one is going to be a 0. Okay? So let me erase those. Didn't mean to erase. Oh! Yeah, okay. I was getting confused what I was doing here because that was in the middle of the bingo board, okay, or the tic-tac-toe board. So I'm going for this position here, which is going to be over here. So we're going to wipe out that row and that column. What is the sign of that position where that 1 is? Negative. So that's going to be a -1 times the determinant of what's left. -3. So that's going to be a 3. All right. Now let's go to the third row to do the third column over there because we're doing the transpose. Okay. So we'll start with 3, 1, which will go into 1, 3. What's the sign of that 1? Positive. So I won't write down +1, and this will be a
3 + 4 7.
7. So this will be a 7 up here. Okay? So this isn't so awfully bad, it's mostly tedious. Not that hard, just tedious. Shouldn't have erased that last line. Write it right back in. Now we're going that position. Any guesses what this one's going to be?
0.
0. You don't even need to ask any questions on that. That's going to be a 0. If I could write a 0. The pen has decided not to cooperate. All right. So let's wipe out that construction line and go to our last one. Okay, that one. What's the sign of that position, the -2?
Positive.
Positive. So that's going to be a -2 times 2. I can't get my pen to write. Negative 2 times 2 is negative 4. All right, let's see how they did in the book. They took probably a lot more time to get there. And how did I botch it up? Yuck. We're nowhere close. Okay, even leading off for the very first one, the C of 1, 1. Did I write it down right? Okay. Oh, I'm sorry. Have I used all our time? Not quite.
7 minutes.
Say again?
7 minutes.
Okay. What I failed to do, I think I do this every time. I get so used to doing one operation, I'm doing a different one. The cofactor has nothing to do with that number there, just the sign of that position. Okay? So let me erase all this. I'm sorry. I made it way harder than what it should have been. Okay? Now, do this, I think, every time because you never use this, well, not really anymore. Okay, it's just a sign of that position, which is positive. And then you just do the determinant of that. And that would be your 4. Right? I'm sorry, you don't use the number there, just the sign of the position. I was doing the minor, okay? Well, that's the minor, but I was doing the whole process there. We didn't want it. The cofactor is just that part of it, okay? So, okay. Now, we're going to do it the same way we did. We went across, so we're going to go down. This. We're not going to use the 3. We just want the sign of that position. What is the sign of that position? Minus. And then we'll do the determinant of this, and that is negative 1. So that's just going to be a plus 1. Yes. Okay. I'm sorry, I was including the number and you don't. You just include the sign of the position, not the number that's there. Okay? So this is truly easier than what I was doing. Okay. So we're doing that 2 there. We're not going to use the 2. We're just going to use the sign of its position. And what is that? Plus. And then do the determinant here. 2. All right. See, this goes a lot faster. We don't have to include any of the numbers themselves. Okay. Let's do this one. Oh, we know what that one is. Oh, no, we don't. Sorry. We're not using the number, just the sign of the position. What's the sign of that position? Negative. And then do the determinant here, and what do you get? Negative 6. Negative of negative 6 is a positive 6. Right. Okay. So the 0 doesn't automatically make it 0. Okay. That's sort of a sad thing because I look forward to those. Okay. Oh, I meant to do the eraser. Okay. Whoa, I lost my middle value there, which I think was a negative 2. Okay. All right. All right. Next is this one. What's the sign of that position? positive. Okay, and then just do the determinant of what's left.
0.
Yeah, and that one does come out being a 0 because the determinant was 0. Okay, very good. Okay. All right. That's a -2 down there. Okay. Now, we're doing this one. We're not worried about the value, which doesn't matter. It's just a 1. What's the sign of that position?
Negative.
Negative. And this would be
-3.
a -3. So negative a -3 is 3. And that's what goes down there. Got it. All right. So once you get the hang of it, it goes a little bit faster. You can get the hang of it. Okay. Now we'll go with the third row, which is going to make the third column. What's the sign of that position of that 1?
Positive.
Positive. And then the determinant is going to be 7. That's the same thing we got before because we're just multiplying by 1, which we didn't need to. I can't get my 7 to right, but there it is. Okay. Okay, now we're going to do this one. And again, don't think because it's a 0 there, it's going to be 0. It's not. What's the sign of that position?
Negative.
Negative. What's the determinant?
-1.
So -1 is positive 1. Okay, one more to go. All we're interested in is the sign of the position of the -2. What is that? Positive. Then take the determinant. 2. There we have it. They got it right this time. Okay. That is the adjoint of A. Okay. Again, you don't use the number, just the sign of the number, and then do the matrix. Okay. I think we probably are close. What have we got left?
1 minute.
1 minute?
Yep.
So let me just write down quickly then what we just did. The inverse, no, this is a theorem based on what we just did. If A is an n by n matrix, big surprise, we're doing determinants, they got to be square, then the inverse of A is equal to 1 over the determinant of A times the adjoint of A. And that's where we use the adjoint. They can be a pain in the neck to calculate, though we saw it wasn't as bad as what I was doing to begin with. But that's another way to find the inverse. If you didn't want to row reduce the matrix with the augmented with the identity matrix, you could do this if this is any easier. We know that finding the determinant is probably pretty easy to do. It's just whether finding the adjoint is easier or harder than doing the row reduction. Okay? That's what it turns out being. Okay? And that's where we'll pick up with example 2. Do we have time for it now? I don't think so, do we?
No, we're out of time.
We're out of time. Okay, so next time we'll start, I'm losing my voice for some reason, with example 2. Okay? I think we may have done enough to do a few homework exercises in this section. Let's see. So try to do, at least find the adjoints. You can try to find the inverses then using the adjoints if you want to. Just an easy step beyond that. So any of the odds 1 through 7. And those should be at calcchat.com. And we'll pick up the rest of those next time, or at least a portion of them. Any questions? sorry I messed up that at the end. That took too long. So what we'll do is go on and close this out. I guess I'll start by